Hello and welcome to my recording of my latest endeavor to investigate free energy and understand it. This video is not so much about theory, I don't think. It's mostly about a circuit that I've been working on. I had some ideas to try out. So if I go find a picture of the circuit, let's see, where's schematic? Schematic off, schematic on. So this may look familiar if you've been following along with what I've been doing up until now. But I've made a few changes because I've taken out... See, this used to be a full diode bridge. Maybe I should go get an example of that, of the old versions, so you can see what I'm comparing with. Let's see, schematic, where's the schematic? Off, on. So I made a minor changes. So I took out D2 diode and D4 diode. And I took out the fuses R7 and R12. These are 1 kilo ohm fuses. And I also took out the R4 fuse. So if we flash over to the new one, the scale is a little different, but other than that, so you see what's missing is here. And then I took this leg, since it had nowhere to go, and I just went all the way back to here, and thus effectively shorted out the AC loop side of the full diode bridge, the AC supposedly so-called input, but of course I do everything backwards, so my AC side of a full diode bridge is the output, because I have the output down here on its way on a branch leading to ground. And I have an earth cap here to represent the Earth's capacitance of 3.25 terafarads, precharged with 1 microvolt, just like all of these down here are likewise. These 10 parallel grounds are also, they have an earth cap representing the capacitance of the Earth of the same terafarad capacitance and charged with 1 microvolt. Because at the surface of the Earth, that's about what the charge is, somewhere in that vicinity, because we can run a crystal radio set in our home a few feet off the ground, because there's about 2 to 3 microvolts available in the atmosphere, coming from, we presume them to be broadcast stations, but in reality it's really the environment. It becomes so diminished, the power from the broadcast station, that it's becomes semi-equivalent to the background voltage that is stored in the airspace immediately above the ground level, put out by the Earth, the plants, us, animals, the weather. Well, on a normal sunny day. Yeah, we have to exclude stormy weather. That changes everything. So I took out those 2 diodes, so now it's no longer a bridge. You know what I'm thinking? Just now I should have taken out these 2 diodes and see what happens. See, but then we'd lose our DC loop. So the whole point is we have a DC loop and we have an AC loop. And the AC loop goes in between the 2 diodes like it traditionally does. And these 2 diodes make sure that the DC loop always goes in the same direction. And so that's all I retained. And so the only thing passing into this DC loop is the voltage from the AC, except this does not generate a whole lot of power. In fact, it's comatose because it's only 1 leg. You have to have a minimum of, let's see, this is 6, 1, 2, 3, 4, 5, 6, so you have to have a minimum of 7 to start to begin to see power gain from the Earth. But it's not stable. So 9 starts to be stable, but I put in 10. And then I put a switch in here to cut off the extra 4 to go back to 6 so that it collapses to a stable off condition. Off being comatose. There's some energy being contributed from the Earth, but not enough to be qualified as free energy, you know, some kind of over-unity gain. And then I have a little bar here representing this is where the Earth is, to separate this portion of the ground, rod, circuit, sub-circuit, from the top portion, which is above ground, and we have our load here, and then a protective fuse of 1 kiloohms. So all these fuses are 1 kiloohms, except for this one is 3 times 1 kiloohm, because I found I needed that to suppress the impedance on the load to get it to be its minimal value, which I found by trial and error to be somewhere in the vicinity of 7 ohms. So the voltage, the VI ratio, the ratio of voltage to current on the load has to be in the vicinity of a factor of 7. 7 times more voltage than current, which means your impedance is 7 ohms. Your reactive impedance. Well, in this case, yeah, because it's a reactive component. So in order to get that suppressed down, instead of it climbing, which I didn't want it to do, I don't want voltage in excess of voltage on the load. I want a, you know, a substantial amount of current, as much as I can put there, which means I have to reduce the voltage. So the whole thing is climbing to infinite gain and is you know, going to blow itself up at some point. So that's why I have the fuses in here, to blow up prior to the circuit being destroyed. So it only costs you the fuse to replace instead of the whole circuit. Hopefully it grows slowly enough that you can manually adjust the power gain by turning the switch on and off. Now, I don't know what happens when you turn the switch off once you've been running it a while. I can only simulate it from presently. My skills have disallowed me from simulating any variety other than from a cold start. So the switch is either off, or I should say it's either open or closed from a cold start, and then I see what happens. And I'm assuming, well, I can't assume. So if you start the circuit on and you get it to the power level you want it, thereabouts, and you pop open the switch to turn off the circuit, turn off the gain, the gainfulness, the gainful acceleration of power, I would imagine that these nice big capacitors here are going to be storing power, because they're a minimum of 140 farads or higher. So they're considered supercaps, I think, when it's in that range of capacitance. And so you're going to get a lot of potential of voltage here. Only one line, that's all you need to transfer voltage to the DC side. And so then you'll have this DC loop going around in circles, giving you power here, and then, well, no, actually you don't need, well, no, it'll maintain this, the current, and this will maintain its oscillations of voltage and also the oscillations here, because you get oscillations of voltage on both sides. You only get a non-oscillatory current on this side. Although it does oscillate, it just goes up and down, but it still stays within a certain range that's very close to being considered continuous current. But since the voltage is oscillating here on this branch, we're probably going to get oscillating power on the load, because both the voltage and the current are going to be oscillating. And that's the only way I know how to do this circuit. Sorry, haven't done any other way. So what I discovered, though, so this was one thing I did. This is what I set out to do, was to get rid of these two See, my problem I was thinking about last night while discussing with a friend, I remembered that when I run a simulation, the time clock of the simulator is communicating directly with every single component, telling it when to do its thing. And so that's not the way things happen in reality. When you've got energy coming from a source and you got a load somewhere else, you've got time lag, and then you get all these harmonics due to the components responding, or receiving, I should say, let alone responding, at varying points in time. They're not receiving all at the same time. I mean, if they're going to respond with different harmonics, that's different. That's, you know, something you can't control necessarily. You just set it up and let it go. But if they receive energy from each other at the wrong time, because in the real world that's what's going to happen when you have it laid out like this, standard convention is you just lay it out, that's not going to work because that's not what the simulator does. So it could be that I have overlooked all my videos describing, or texts describing, showing how to build something. No, it's just this. It's only good for the simulator. It's not good for building. And one of the things I may have overlooked, besides the inclusion of iron in all of the coils to conserve against magnetic loss, to follow the legacy that Oliver Heaviside has left us when he solved the transatlantic telegraph cable problem of the 1800s. The other thing, in addition to that, is that any switching component has to be in sync with any other switching component. And when I say switching component, it's a certain type of component. That means capacitors, diodes, switches, anything that causes a reversal of polarization of either voltage or current or both. Now coils do create a back EMF, but it's not a switch in the sense that you don't get a reversal all at once. You get a gradual catch-up. The current has to catch up due to that switching action. And so I don't... And plus, anyway, why don't I just be frank? I never found it to be a problem if coils are out of sync. So I never bother... In other words, when I did that experiment, that biocircuit experiment 9 years ago, I found that coils don't really need to be synchronized, but the capacitors do. And because diodes function similar to a switch, and a switch has both spark gap and capacitive characteristics to its behavior as you open and close the switch, the contacts move close together. That's a parametric variation of capacitance. They move apart. That's another parametric variation of capacitance. And if they get close enough, you'll get some sparking. You won't see it, most likely, but it's there. When you draw them together, you're closing the switch, or you draw the contacts apart when you're opening the switch. So you've got elements of capacitance, variable capacitance, and elements of variable spark gap distance. So it's a very complicated affair, but it's a switching action. And so it better be synchronized. All of your types, like your diodes should all be synchronized with each other, your capacitors synchronized with each other. And so when I look here and I see, oh, well, I got 4 diodes, I got 4 diodes here, I'm going to have to combine them. But how do I combine them? So I logically, without eliminating anything yet, just the act of combination, I thought, well, the logical combination would be to add this upper left, D1, to the lower right, D4. Because when let's say the AC half phase is, the current is coming in from the left here, on the left-hand side. So that means it's going to go up here, up through D1, and it's going to be pulling out here, which means it's going to be drawing up current through D4, and D2 and D3 are just going to be sitting there not doing much of anything. They'll be kind of comatose. And then when the AC goes in reverse, it's going to be coming in here on this right-hand side, which means now D4 is comatose, and the current's going to flow up D2. Meanwhile, it's pulling out on the left-hand side here, which means D1 is going to go comatose, and the current is going to be drawn up through D3. So I thought to myself, okay, I should pair off D1 with D4 and D2 with D3. But now how do I tell the simulator to do that? Oops. Well, I can't. I don't know how. I mean, if I built them, maybe I could, but I can't do it under simulations. So the best I could do was to simply take out both of these diodes on the right-hand side and bring this connection on the right that's just hanging there over to the left-hand side and short out the AC with itself, the AC loop. And that was the best I could do. But it turned out I didn't need those 2 diodes. So it's always good to simplify a circuit after you've gone to the trouble of making it complicated, because it's easier on the simulator. You get less error messages. It's less stressful on the physical build because you have, well, I'm assuming it's less stressful. If it's less stressful on the simulator, then it's less stressful. I don't know. It's just better to simplify, right? But I found that I also had to take out this fuse up here because it was a duplication of fuses I don't need. I only need one up here on this leg. And then it wasn't good enough to suppress the impedance of this load. The voltage was getting too high relative to the current. But when I did the multiples of this, I did ×2, and then when I hit ×3, I got the suppression that I had previously had when I had all of these diodes and the extra fuse sitting over here. I got the same amount, around 7 ohms on the inductive load. So that was an adjustment I had to make. So I highlight it in red so you can see. Everything else is the same except I took out the 2 diodes and this extra fuse over here that was 1 kilo ohm. Now the power level was roughly the same. So I did one other thing to make things interesting for myself because, you know, I don't like being bored. And that was I ran across let's see, I ran across in the help file, the microcap help file. Oh yeah, well this one, first I tried to do a harmonic analysis. Microcap allows you to do various types of analysis, and harmonic is one of them. And I got an error message. Sorry, you can't do it because you don't have a source. So, just to highlight, you know, the fact that this circuit does not have a source, you know, all I do is pre-charge the capacitors that represent the earth. So I'm using the earth as my source. The constant supply of microvolt voltage difference between the ground and the space, the airspace immediately above ground, a few feet above ground. And that's it. That's all the power I'm running off of. So then I tried a different type of, because I wanted to try different types of analysis to see what I was missing. And then I came upon this. Oh, this is so interesting. Power and energy. See, normally I tell the circuit to give me the power output. I do so because I'll take the voltage times the current if I just want the raw power. But if I want the RMS, I'll do RMS of the voltage and then separately multiply it against the RMS of the current to give me the RMS wattage. And you have to do that anyway if you use their total power function or total energy function. But I didn't know, I kind of knew, but I never really, I don't know. I just don't bother to use all the features that microcap has, and it's probably my loss and yours. So I decided to use. You can use PGT if you had a power source, which I don't. So it allows you to use PGT. What you do is, I'm using RMS. I have RMS here times of the voltage on the ground cap times the RMS of its current, and then I multiply it against the raw power, not RMS, and I test to see is this greater than or less than 0, and then I turn it into a -1 or a +1, and I multiply it against the RMS, because RMS is always positive value, so I want it to be positive or negative depending on whether or not the raw power was positive or negative. But it turns out to be positive, which means that I can't find any component that's generating power, you know, generating negative watts. All the when I have the load there on the left-hand side, the diodes stop generating power. They stop generating negative watts. And instead, all the current gets sucked in from the earth. Whereas if I have no load on the left-hand side in the schematic, when I have this branch here not here, and it's just floating, and I only have the ground on the right-hand side here on the DC loop, and so it's no ground on the AC side of these diodes. When I only have it here on the right-hand side, then what happens is the diodes become generators. But I had 4 diodes here when I did that experiment. I didn't try it on 2. And the branches here, the grounds, do not pull current in. They're actually sending an excess to the earth, coming out of the diodes. The diodes are acting as generators of power. But if I put this ground here on the left-hand side connected to the AC loop, Then the diodes stopped generating, the 4 diodes stopped generating power, and all of these 10 ground branches and the load branch here, the 11th one here, they all suck current from the earth. So I'll assume that that's maybe what's really happening, but I don't really know. Both could be happening. We could have generation of power going on in the diodes, as well as current being sucked in from the earth. Who knows? I don't know. What do I know? But that was an interesting experiment that I performed. So let's see. So I got to move down here. So if you use PGT or EGT, you won't get an error message, even though there's no source. You know, because that's what it would be doing. It would be focusing on the source. So because there's no source, the outcome is very interesting. It shouldn't be surprising. Let's see, on total energy. It should not be surprising because, as it turns out, it's 0. In red here, see? PGT, EGT, watts, joules. It's 0. And trust me, I did the number version to see what it is numerically, and it's 0. It's not even close to 0. It's just flat out 0. And it didn't give me any error messages. Imagine that. But then I did, now the storage, now according to, let's see, if we go back to, why do I have 2 of these? That's interesting. Okay. So if you go into, storage, PST or EST, that's energy or power or energy that's stored in the inductors and the capacitors. And so that's S. D is the dissipation through resistive components, such as diodes or resistors. So, if we go back to here, so the PST, the watts, or the EST joules, the storage, would be caps and coils. Well, I have some coils and I have some caps, right? So here's a coil here, inductive ballast of 1 microhenry. Here's the inductive load of 10 henries. And then I have these capacitors here of 140 farads. I have the ground cap, which is, what's the ground cap? It's the same as the adjustment cap, 100 femto, a tenth of a picofarad. And then these adjustment caps, again, a tenth of a picofarad for each one of them. So you're not going to find a tenth of a picofarad to shop for it online. So you just have to buy 10 picofarad capacitors and string them up in series so that the total capacitance of all 10 of them is a tenth of a picofarad. Of course, you're going to have solder joints between them, and that's going to add resistance, and I don't have that in this simulation, so you may get different results. You may not even get over unity. So maybe you'll have to construct your own tenth of a picofarad capacitor from scratch. Be that as it may, there are ways of doing that. There are people online who tell you how to do that. I think one guy, he used polyethylene plastic for his dielectric, and he used 2 metallic plates for his conductive plates, and he immersed them into a vat of oil and shook them and waited a while for all of the bubbles to rise to the surface. I guess it was mineral oil. And then he put a vise, a C-clamp, in there and pushed them together so that the plastic would make union with the plates. But there were no bubbles because he made certain of that. So if there was any residue, it was just a thin film of oil in between the plates and the dielectric. So there are ways of doing it. So the storage is in all the capacitors, and that includes the earth capacitors as well. You know, and they're going to be storing a lot of power. So even though we don't get to see it or use it, it's there in the earth. And so the PST wattage rose to a value that is somewhere in the vicinity of, I think it's 5e to the 36. So, you know, something more than 10 to the power of 36, slightly more than. Well, that was the joules, actually. the wattage was down closer to 1 e to the 36. So the energy wasn't much bigger, but it was slightly more than the power. Now, the dissipation in the diodes and resistors was less than what's being stored in the capacitors and coils by this factor. So that's why I did this relationship here of PST divided by PDT. But the PDT, the energy, the joules dissipated is e to the 25 by comparison to what was being stored, e to the 36. So I took the average proportionality and I got 600 giga joules or gigawatts as my limit on the graph, but the actual bar here is less than, it looks like 450. So it's probably 425 gigawatts or gigajoules. And they both are pretty much the same as each other because I'm taking a proportionality between storage and dissipation. So it comes out to be the same for both power versus energy. Or, excuse me, for both storage and dissipation. And also for energy versus power. Then I decided to take that value and divide it by what's being generated, just to see what would happen. Now what's being generated is 0, because there are no components. Yet the simulator must have decided on its own, well, I'm not going to divide by 0, and I'm not going to give him an error message, because I already allowed him to do the power and the energy. So now I am forced to take the division. So it must have assumed a very small amount, because it ends up being in the vicinity of 4.5 times 10 to the 61st power. So 10 raised to the power of 61 times 4.5 is the gain, the factor, the COP, the coefficient of performance between the source and the power left over after dissipation, you know, what power, the storage of power left over minus or divided by what's dissipated. Or maybe I should have subtracted. Oh no, I was looking for ratios, right. So it's not minus what was dissipated. It should be, actually, when you think about it. Wouldn't you? That means it would be much higher than this. It'd be closer to e to the 25, actually. But I was looking for proportionalities. I wonder if that's right, if I should be doing that. Well, no, storage versus dissipation, that's a ratio, that's good. But is that what I want here when I take that and divide by 0? Divide by the source. Maybe not, I don't know. Well, it would be something bigger, though, if I did PST minus PDT and then divided that by PGT. Should we do that? Let's do that and find out what happens. Probably going to get another warning message. The screencast doesn't like it when I overload my computer. So, if we go into, which one is this? This is on. Okay, so we go into transient analysis. And we change this figure here. Where are we here? So this should be minus. Okay. All right, let's see what happens. Okay, so now the only thing that's changed is our quantity of power and energy. Instead of e to the 61, it's e to the 86. Otherwise, the numeric value is the same, but the power value, or the power of 10 value, you know, how many place values to the left of the decimal point, has increased from 61 to 86. And this is in the course of just under half of a kilosecond. So it takes about 500 seconds to get this gain, and so there should be plenty of time to operate a switch to manually adjust to get what you want, I would assume. Now, if you like, let's try that. Let's try a different time frame. There you go. So that looks good. 150,000 watts, right? So if I go up here, the right-hand side is 140,000 watts. So you get 140,000 watts in 336 and a fifth of plus a fifth of a second. So if you really want to tailor it, you really have to get in there into tenths of a second. And, you know, if you've got some kind of Arduino or something, you know, a microcontroller controlling your, turning that switch, that manual switch on and off to regulate your power, from a cold start, that's what you'd want to do. You'd want to shut off something slightly less than 0.2 seconds, and you'd only have an excess of power by a small amount. I mean, if your target, see now, my EV from 2002, the RAV4 EV, requires at full throttle around 67,000 watts. So 140,000 is about twice of what you need, which is not bad wiggle room to deliver slightly more. Well, let's see what 0.1 would do. I'm curious now. It's not even close to there. You'd have to do it in a fraction of a second. That's like 150 milliseconds on top of the 336 seconds to be able to. It's not enough. Oh, it's close. It's getting there. Ooh. So it's somewhere in between 180 and 190. So if we find out exactly what it rose to 78.9, so around 80,000 watts. So, and that ran for 336 seconds plus 190 milliseconds. So you could do it, you know, if you could operate this manual switch fast enough, you could cut things off and get the exact power gain you want to, and then these capacitors would hold on to it and hopefully keep feeding your inductive load and you know, as you dissipate the power, then you won't have to close the switch again for a certain length of time to get more power. Now, of course, this is not an EV, is it? This would be your home, let's say. So I haven't, but it wouldn't be much different than this in composition, the circuit in composition, in structure, because I just put in these earth caps for reality check, and they do undermine the power gain, but they don't prevent you from getting over unity. They just undercut it by a fraction, really. It's a tiny little portion. So it's not much of an impedance to over unity. It certainly doesn't turn off over unity. But I don't know if that's the case when I reduced it to 2 diodes, because I developed the circuit under 4 diode condition, not 2. So I don't know what it would be like with 2. Anywho, that doesn't mean you have to build this thing with only 2 diodes. Maybe you have to build it with 4, you know, the previous version that I showed you. Anywho, let's see, is that all I want to say? So it might be possible to have a variation of this circuit that's totally mobile, that you can take with you in your EV, powering your EV. And so you would take away this earth cap as well. And so this would be one aerial, and this would be 10 others. I would imagine, for this to work. But, well, I don't know. See, reality versus simulated virtual reality, I don't know. All I can do is say, well, you know what? This looks nice, and maybe somebody gets motivated to build it and see what actually happens, rather than what Vinny claimed his simulator made happen. But you do want fuses because that's just safety. You know, you're building the thing, and maybe you left the switch closed, and you made all your connections. You didn't realize the thing is on while you're building it. Oops. So you want some fuses for safety's sake, for at least for no other reason to help protect you, if nothing else, but also, of course, to protect your circuit. So you only have to replace the fuses, because you got to stay on top of the switch until you figure out some mechanism to regulate the switch based on sensors. If you have to run it manually, you got to be pretty careful, and you got to probably put all of this inside of a plastic case with a lid, and because when the fuses blow, you don't know what's going to happen. It could send shrapnel in all directions. Or maybe you just have to put encasements around the fuses, but the encasements have to be pretty ridiculously strong so that the encasements don't fragment into shrapnel pieces and fly in your face, embed themselves in your face, your pretty face. We don't want that to happen. So you do have to take certain, and then the electrocution problem, you know, there's that too, because the nodal voltages are humongous, just to give you an idea. Well, I mean, look at that. I mean, we're talking, these are humongous, and this is a reduced time frame of 336 seconds, plus a little extra. If you run it to the limit of microcap's ability to continue to simulate, these values up here get to be e to the 24. So the nodal voltages are huge. But even this is huge. Teravolts, mega, you know, so you're going to, well, this is below the Earth, so it doesn't count, but it's above the Earth, it starts to build up, especially right here and here. Now I noticed that when you do current flow diagram, a very interesting thing happens. Notice how all the arrows are pointing up here, and they're also pointing up down here. But it's pointing down here and down here. It's up here, so apparently it's going around in a circle, except here. It's going back the other way. So from this point, it's going here and then down, and from this point, it's going this way. So it's coming out simultaneously from this single point. Meanwhile, oh, this is doing the opposite. When it reached the limit, it went the other way. But now this is going around, circulating in this direction. And see, the current is coming in through the load from the Earth, and it's coming in from the Earth down below here and up here as well. And then it's coming down here, and then it congregates right in the middle. So this branch is going to get two currents jamming up into it, which is why the voltage is so high. When I showed you the voltage, it was so high up on at the top side of these caps, because it's building up right in this leg here and up in here, these connecting branches up at the top of all of these grounding rods. So all this voltage is building up because current is coming in from here, and it's coming in from all of these 10 and bunching up an accumulation of voltage around in here, in this area right in here. So it's a little strange, but it also tells you where your weakness is. If anything's going to blow, it's going to be here, but you can't put a fuse there, unfortunately. It ruins the over-unity. You can only put fuses up on your AC loop and your DC loop, and then on the ground branch going to your load, the load branch, the load ground. Because on your earth grounds, on the right-hand side, on your DC side, you cannot have any resistances greater than a solder joint. This is a limitation of all of this, and that's how you get the over-unity, by allowing voltage to build up here and current to do some ridiculously weird things in its flow patterns. So it's interesting. So this kind of got me stimulated to think, well, what else am I missing? And so then I ran across the total power, total energy functions that microcap affords us. Here we have power. And so I wondered, well, what does PD mean and PS? And when I looked it up, then now I know. So PD means what's being stored versus PS means what's being dissipated. So in this inductor here of 1 microhenry, the storage, no, excuse me, the dissipation is 2 watts, and the storage is close to 30. So it's storing 30 and dissipating 2 watts. Meanwhile, this fuse over on the right is dissipating 2 gigawatts. This capacitor is storing 10 to the power of 19, but it's dissipating 6 times 10 to the power of 6. It's dissipating far less than what it's storing. So it's no wonder this thing grows in power. You know, it's storing 10 to the power of 19, but it's dissipating 10 to the power of 6. So yeah, that's a lot of storage. Now here, let's see. Well, this is pretty small. 50 nanowatts is being dissipated in this fuse over here. Now on the load, we're getting a storage that's 300 times 10 to the 6th power. Meanwhile, we're dissipating 12 times 10 to the 6th power. So it's 12 versus 300. 12 is being dissipated and 300 is being stored on the load. It looks like the earth, or the caps, the adjustment caps above the earth, they're the same as the ground cap over here. Yeah, it's pretty much the same. While the earth caps are storing slightly more than half of a microwatt, but they're dissipating close to 6 times 10 to the 6th power. 6 megawatts, close to 6 megawatts. So they're dissipating close to 6 megawatts, but they're storing a mere half of a microwatt. So the Earth isn't going to accumulate any energy to speak of, which is good to know. So you're not going to mess up the Earth and cause weird ground currents or something. Wait a minute. Oh, no, you are, because you're going to be dissipating. Oopsie. Yeah, you're dissipating megawatts of power into the Earth. That's why it doesn't store it, because the capacitance is so high, I guess. It makes just it doesn't make much of a dent on what the Earth is being asked to store. But it is dissipating. So where is it dissipating it to? Oh, to itself. Well, that's true, because these caps represent the Earth, the capacitance of the Earth. But it's rooted in the ground connection down here. So you are going to get a lot of ground currents. Let's go back. Let's see. Well, it shows only 1,000 amps is coming in there. Well, that's not a lot. So it's mostly voltage, though. So it's watts, but it's not a whole lot of ground current. It's mostly just voltage is being dissipated. You know, when we look at the wattage, 6 megawatts, mostly that's voltage being dissipated, not a whole lot of current. It's only kiloamps of ground current that's being dissipated. Now this last button tells you the condition, and the only components that the condition it's going to tell you are these diodes. They're hot because they're on. You're using them. So they're probably going to fry. So in a sense, those are your fuses too. They'll probably blow before your fuses blow, or maybe the fuses will blow before your diodes blow. Who knows? All depends which kind of tolerance, level the diode that you pick. If it's a high voltage, high current diode, mostly it should be high voltage. Because if we turn that off and we go back to current, it's only a kiloamp going through a little slightly more than a kiloamp going through this diode. This one, it's 7 microamps. So it's only this diode that has to suffer a lot of current. Meanwhile, when it comes to voltages, though, we're talking megavolts. But it's on both sides. See, so it's not really a voltage strain. Because if we look at the power, the dissipation, though, is giga. I don't get to see the... well, wait a minute. No, I can. Where is it? PS. Where are you? PS. V. 1 volt. Oh, PD. No, PD is... No, that was the current. Oh, shoot. It doesn't tell us. Voltage difference. Oh, 1 volt. Oh, is that what that is? 1 volt? Huh. PS is 0. Oh, the power. Oh, so the power stored is 0. Wait a minute, I got 2 different values. Oh, this is on the resistor. I'm sorry. So it's 0. That's why it doesn't list it. It only lists the dissipation of the diode, which was 1,000, about 1,400 watts, kilowatts. So, okay. But it didn't tell us the voltage, though. Oh, no, it was 1 volt. Yeah. So these are not high. The diodes won't fry. It'll probably be the fuses will fry. Okay. Well, that's enough said, I guess. Well, that was fun, huh? Alright, so this second segment, I need to add in because I forgot to say certain things. So we'll start off with this. The conservation of energy is at the expense of the conservation of our perspective. Conservation of energy is upheld whenever time moves backwards because we have not touched energy. We have merely altered time by reversing the polarity of current relative to the polarity of voltage. Whenever time moves forward, the polarity of current is in alignment with the polarity of voltage, and energy is entropic, namely, it diminishes with time. But whenever time moves backwards, energy continues to diminish, but in reverse of our perspective of time, making it appear as if energy is increasing when it, in fact, is not from its perspective. Only from our perspective does it appear to increase, but our perspective does not count. Only the perspective of energy is important whenever we consider whether or not the conservation of energy has been upheld. So the conservation of perspective has not been upheld since we have altered our perspective via the reversal of time. So from a practical consideration, who cares? You know, it's only the physicist that would care about conservation of energy. We just want the benefit, which is the extra gain coming out of the device by comparison to the energy we fed it. And that's in deference to whatever happens inside that so-called black box of a device. Who cares, right? But if you're designing it, and if you're trying to prognosticate or advertise, promote. If you're trying to promote the idea of free energy, especially to conservatives, how do you go about doing it? Well, by claiming that conservation of energy has always been upheld, it's just perspective that gets twisted and tweaked, which relativity in physics allows for, because you send two twins, you send one of two twins in a rocket at the speed of light, and he comes back, and you compare the watches of each. If he comes back soon enough before his brother dies, then you find out that the guy who went in the rocket didn't age, while the guy on Earth who stayed behind aged considerably. Well, time has been sacrificed because perspective has been sacrificed, yet energy has been conserved. And it applies to the reversal of current just as much as it applies to the reversal of time, because the reversal of current is nothing more than the reversal of time and vice versa. It's the same thing. From the standpoint of energy, now we haven't done that to the material object. We have only done that to the energy. And one of the things I tried to pursue but didn't get anywhere with was this idea that if you take the square root of both sides of E equals mc squared, maybe you get something. And it doesn't look like it. But Eric Dollard has said that the relationship between mass and energy was discovered by Maxwell to be the square of the speed of light. And that doesn't mean, see, we took it to mean, we inferred something from that. We inferred that that proportional relationship is actually the speed of light. Correction, according to Eric Dollard, it wasn't mass versus energy. He was looking at the dielectric force versus the magnetic force, which lends or suggests some relationship between the dielectric force and energy and magnetism and mass, or the other way around, actually. Yeah, I think it's the dielectricity is mass and energy is the magnetism. Because magnetism is what we want, because that's the useful thing, and so is the energy. Where I got this from looking at some analysis that I did of my circuit. And this is the circuit when it's on. So the switch is closed here, versus, I'm sorry, I didn't get these in advance. Versus when it is off. Here we go. Okay, so we open this switch and then we lose 4 grounding rods, and the circuit's gain turns off so that it's not gainfully over unity anymore. Okay, but if we have the circuit closed, then it's gainful unity. So what I did was I did an analysis, and I came upon a oh, now I gotta look for that. Oh, here it is. So I found this in the help file of microcap 12, and it's kind of interesting because it says you can do an analysis for the entire circuit, its power and its versus or its energy. You can also do individual components, but I didn't get anything useful out of that. But I did get some interesting information out of doing the entire circuit. So since I don't have a source, I did it anyway because I pre-charged capacitors. So if I show you, right, so all of these earth caps down here, the 10 of them, and this one over here underneath the load, the inductive load, they're all charged with IC means initial condition is equal to 1 microvolt. The little u here represents a micro symbol for 1 microvolt. So it's a pre-charged capacitance of the earth, and it's 3.25 terafarads, e to the 12 farads, on the presumption that the earth is hollow, whose shell is about 1,000 kilometers thick, more or less. All of my solder joints are 1 milliohm, but my fuses are 1,000 ohms, except for this one, which is 3 times that value, 3,000 ohms. Anyway, so when I found this, I decided, okay, I'm going to take these measurements. So when I took them, if I can find out which one, whoopsie. So, whoops, wrong one. Okay, so when I took them in the on condition, I found that, so this column here represents everything on the left-hand side of the graph. It's this label right here is pinning this column to the values that were at nearly the beginning. It's actually 134.5 seconds. Is that right? No. No, according to this, it's 2.690 seconds. Why does it say that? Oh, no, that's just the column division. Oh, I'm sorry. This is a numeric graph, and I have to avoid the graphical graph. Okay, these numbers, see, 2.690. So at 2.7 seconds into the runtime, you get the values that are in this column, while at the terminus over on the far right of 336.19 seconds, you get the values in this column. So I tend to pay attention to these two columns because this tells me what's over here to the far left, and this column tells me what's over here to the far right. And I get to look at the difference between them. Start time and end time, what was the, in this case, the power and the energy levels. Now the inductive load, no, excuse me, the capacitors didn't have a whole lot of energy. It's minus to the 22 power of 10, you know. Capacitors didn't accumulate, but they are, you know, the wattage is rising up there. The load is also, and I terminate it just on the mark so that I get 78.914 kilowatts on the inductive load. The inductive load being this coil right here, this 10 Henry coil, and here are my two capacitors. I just read out to you the minuscule 10 or 10 to the power of negative 22 wattage. Anyway, so going down the line, then we get to the power of the source. Well, the source is 0 because there is no source, so it's 0. And so I get to say here, time stands still. Oh wait, let's build this up so you can see it. Time stands still when energy is 0, since there is nothing to conserve. Ha ha ha. Okay. So these are my basic, what do you call it, relationships. So total means total simulation runtime. In this case, 100,000 seconds. No, I'm sorry, that's old. Oh shit, I gotta sorry. I gotta change. Oh, I screwed myself. Dang it. Dang it, I ought to get a rope and hang it from the highest tree. Oh no. I should stop this recording and change all of these things because I am all messed up. Sorry, dudes. I gotta restart this. Alright, now I'm better prepared. Alright, so the runtime for this simulation is 336.19 seconds. Let's see. So, what I did was I discovered that, let's push this over. Yeah. So the power source, so ignoring the source, actually, this is the source up here is 0. So PST is the storage, PDT is the dissipation of power, and E is for energy. So the simulator is assuming that the quantity of energy, the total quantity of energy that's stored in the circuit is its wattage, while the total quantity of energy stored in the circuit is its joules. Excuse me, the total quantity of energy, the total quantity of power stored in the circuit is the watts, while the total quantity of energy stored in the circuit is joules, versus the total quantity of power that's dissipated. So storage means in inductors, coils, and caps, while dissipation are resistive elements such as diodes and resistors. So it kind of segregates what's going on. It's not the total circuit. It's just specific types of components. So what I discovered is that if the sign value, the polarity of the sign value is the same, in this case they're both positive, then time is moving forward and everything is normal. Well, this is at the beginning, towards the beginning, at 2.7 seconds. So this circuit is on. So when the circuit is on, it's behaving normally in terms of what's stored in the caps and coils, and what's dissipated in the resistors and the diodes is also normal. It's forward, time is moving forward because current is in alignment with voltage. Also, when I take the ratio between what's stored and what's dissipated, again, and then compare power versus energy, it shows that both sign values are the same. That means, see, when it computes the energy, it takes power and divides by the time interval. And the time interval can vary from one period of interval to the next. It recalculates what interval to utilize. So it keeps changing. So at this particular point in time, at 2.69 seconds, the time interval was computed to be positive, because when it took the power, let's go back up here actually. When it took the power and divided by the time factor, then it got the energy, and it's the same sign value, showing that the time interval was positive. It had no impact whatsoever on altering the polarity of power when converting into energy. And that's the same for down here and same for here. So everything, when the circuit is turned on, the circuit behaves normally. But when the circuit reaches its maximum of 300, in this runtime simulation of 336.19 seconds, things change. So this value was what's stored in the caps and coils. So now the time is backwards for storage, but it's forwards for dissipation. So it's dissipating in a normal way, which you'd kind of expect for resistors and diodes, right? They're not going to do anything weird. But the caps and coils are generating power, according to this, because the time is going backwards. Now, that's for storage. For dissipation, though, see over here, dissipation? Now, it's the same as at the beginning. It's forward time because the sine value is the same. But here we get differences because I'm doing ratio proportions. So here I'm trying to compare what is stored versus what is dissipated. And of course, in the beginning I'm dissipating more than I'm storing, right? But when at the end, I'm also storing less than what I'm dissipating, but it's negative. Okay, so I'm dissipating more than what I'm storing. Isn't that kind of interesting? So there's a difference here of like 34 joules by comparison to the watts. Well, 34 gigawatts missing. So time must have had something to do with that. I don't know what, quite frankly. Oh, I see. No, that's the time. Oh, right, that's why there's a discrepancy. So the time interval makes up the difference between the discrepancy between power and energy. So I'm sorry, I'm new at this. It's all new to me, power versus energy. Now when I compare I subtract, now I do it differently. I don't divide. I subtract the dissipation of power or the dissipation of energy from the storage of energy or the storage of power, and I compare it in ratio to what's generated, which, if you remember up here, was 0. Okay? So I would expect to get a warning message, I cannot divide by 0. No, instead, I get this humongous number, so it shows that it's not really 0. The time interval, well, no, right, it's not really 0. So where did that extra energy come from? Probably from the pre-charged capacitances. See? It's good to make a video because then you realize, where is it? You realize what you're overlooking. So the pre-charged condition of the earth caps is all 1 microvolt. So I am starting out with a certain amount of energy. And for some reason the circuit, the simulator is deciding, oh, you know, you don't have any generators, so I'm going to tell you it's 0, but I'm going to use the value in the circuit, apparently, or else it would have given me a warning message and say I can't divide by 0, and instead I get this humongous number of the comparison of what's, you know, the total gain factor. This would be like the COP, right? So here I'm trying to find out the coefficient of performance, and of course it's ridiculous. It's up there 10 to the 70 for power and 10 to the 69 for energy. But so now our energy is greater, no, excuse me, our power is greater than our energy, so the time factor must be having something to do with that. The time factor must be something less than 1 second, but very close to it. And that's the case also when it starts out here. But it's negative. So the power is still generating power, but it's not generating energy, which means the time factor is going backwards. And also likewise here, the energy is positive but the power is negative, and so the time factor must be negative. It's going backwards in time. And here we get it, we see it rises up. Do I have the no, that's the wrong one. See, this is what I was trying to do, but I got nowhere with it. Okay, I didn't. Alright, skip it, I can't find it. Now this is when it's off. Now this I actually bothered to compute some of the values, but I got lazy and I didn't want to do it anymore. So here again our generation is 0, and the off condition, if I can remind us, what is the off condition? This is the on. The off condition. So the switch is up, okay? So that's the off condition. And generation is still 0, but now the end run, the end time for this simulation is 100,000 seconds. The other was 336.19 seconds, because I was trying to target how much energy I want the thing to cut off to run my EV, my RAV4 EV from 2002. Here, since it's off, I want to run it much longer to make sure everything zeroes out. I don't want any what do you call it, confusion. You know, is something still rising? Well, I better take the simulation to run longer to find out, does it really come back down towards zero, or does it keep rising? Because if that's the case, then I had to learn to see, when I was constructing the circuit in the off condition, I had to pay attention to everything going downwards, because I wanted to make sure that I had the correct number of grounding rods to the right of the switch here. You know, so I determined I needed, or let me put it this way, I needed the right minimum, or excuse me, the right maximum of grounding rods here to ensure a stable off condition that did not rise, kind of creep up, rise, you know. So I determined it was 6, you know, not 7, not 8, not 9, but 6. So that was the purpose of running it so long. Now, I did actually get some values, so I did some computations. So, if this is what? Well, let's do this one first. See, I did the computation here, so I actually do it instead of refer to it being done. I did it by hand. So we get the storage of power versus the storage of energy. So here we've got, I figured out what the time frame was for these values. So here's the power being stored in the caps and coils. It's negative 0.2388 nanowatts. Meanwhile, the energy being dissipated through the diodes and resistors is 2.873 nanojoules. So the unit of measurement is slightly higher for energy dissipation versus the power storage. But the power is negative. So that tells me that time is going backwards. And so I have negative 0.8312 milliseconds, about 800 milliseconds. But it's negative. Oh, I didn't put the negative sign in here. Darn it. Can't seem to do everything right. Darn. That was supposed to be negative here. Now I'm going to have to redo this. Oh, shoot. Okay, moving right along. Let's see. So to get that figure, I had to take negative 2.388 e to the negative 12, or approximately 2 picowatts. That's not right. It's nano. Oh no. Don't tell me I did the wrong computation. I did it wrong. It's supposed to be e to the negative 9. Uh-oh. I've made a lot of errors. I think I'm going to have to stop the video now and I keep finding these mistakes. What the? Did I do anything right? Yes, I did this one right. This was the only one I did right. Okay, at the termination of the runtime, and this is the off condition, time is moving forward. But in the beginning, it's moving backwards, according to this computation. I just had the wrong power here. The sign value is correct for time. Time is moving backwards. But that's at the beginning of the circuit. So in the beginning, the circuit tries to create over unity, but it's not a whole lot. It's in the nanowatt and nanojoule range. But at the end of 100,000 seconds of runtime, now it's definitely forward-moving time. So everything has been dissipated because the sign values are negative, both the power and the energy. That means time is moving forward because time was positive. So that was the purpose. First I tried to calculate, and I guess I couldn't keep it up. I made mistakes, so I gave up. Subconsciously, subliminally, I must have realized I better just look at the sign values and forget about the numbers, because you don't need the numbers. That just tells you what the time value is. And it's good. I did it one time, but I'm going to have to redo that one because that's a mistake. I didn't even try to do it on the on version. I just did it on the off version because I did the off version first, and I got bored and tired of doing all the calculations by hand. So I only have this I also forgot to put a negative sign in here. I just put a wiggly mark showing that it's approximately 100 picojoules. Joules? Oh, I calculated it differently. Here is the seconds, 10 femtoseconds. Oh, I did everything upside down and backwards. Yeah, not even consistent with myself. In any case, these figures are correct, even though the circuit is not nice and tidy with the seconds on the outside of the equation. Yeah, I should be joules divided by watts gives me the seconds. That's true. Well, I might as well redo this part then, if I'm going to redo that. Anyway, so moving right along. So in the off condition again, so here everything's the same, here everything's the same, here everything is the same value, same polarity value, but only in the beginning is it different, but not when it's being dissipated. It's dissipating in a normal way according to thermodynamics, but when it's storing it, it's trying to generate energy and power, or power and energy. Well, I decided on not making any changes to this video. I think I've said and done enough. This is the shortcut URL to download it from ufile.io. 10YR64R. And I guess that sizes it up. So I probably did a lot of hemming and hawing. I'm probably going to have to edit that out. But basically, microcap 12 will tell you when time is going backwards, when the current is going in reverse to voltage. It will also tell you negative watts if you do your analysis that way. And that also tells you that current is going backwards. But I think it's pretty bizarre that time goes backwards. And Eric Dollard has talked about it. I never thought I'd bump into it. I thought, oh no, only Eric would witness that, not little p on me. But here it is, simulator. The microcap simulator is showing me a reversal of time. So I'll finish this with this one last thought. The Big Bang is not required anymore. Now, and nor are black holes and humongous gravity. A reversal of current and reversal of time explains both. So when you have a black hole, the light is going backwards. The voltage wants to send it out, but the current goes in reverse back towards its source. So it's a black hole. And big bangs are not necessary because time, you don't need the universe to collapse into a Big Bang after it has already expanded. You simply, every single particle in creation has the opportunity to either go forwards in time or backwards in time. And the integrity of the particle itself does not have to go, at least I haven't seen it, does not have to go through this kind of reversal of time. In fact, I suspect that time does not impact matter. It only impacts energy. So only energy can go forward in time, and only energy can go backwards in time, because energy is what transforms matter into something else. And so only energy can go backwards, while the matter itself does not. Now the difference between the two is a difference of squaring. And it has something to do with taking the square root of E equals mc squared, gives us energy, while the square gives us matter and inertia and gravity. Because there's a whole nother level to matter that's linear and simple and straightforward, I think. This is what I'm guessing. This is speculation now, because it would give us wiggle room to do whatever we want, and still not have to dissolve the universe in order to do it. But the dissolution of the universe would have to, it's not a Big Bang, it's simply a portion of the universe, because it's made to look like it goes away, because its energy is made to go away. See, energy needs a host, but if the energy should diminish in size, then for all intents and purposes, it looks like the matter has disappeared. So matter doesn't really exist, okay? There's no such thing as matter. Particles doesn't exist. The only thing that exists are waves and frequencies and energy and the dynamics. So it's illusory to think that there's such a thing as matter. So everything in creation is a verb. There's no such thing as a noun. And everything in creation is not an object, it's a subject. It has consciousness. And so that means it's subject to shifts in perspective, which we've already seen. Time can go backwards. But the only reason why time is going backwards is to accommodate the energy. The current. The current is going backwards with respect to voltage. I do create this situation using reactance of caps and coils, but it's not your standard tank circuit in which there's a limit. Because people always look at caps and coils as individual components. They never look at pairs of caps and pairs of coils working together in sort of, or multiples, let's put it that way, multiples of caps and or multiples of coils, because it changes everything when you deal with them in multiples as opposed to singularities. And this is why electrical engineers fall flat on their face, because they don't appreciate the dynamics of two capacitors bouncing off each other, or two coils. It changes the whole picture, like night and day. It's the difference between whether or not you can achieve overunity or whether or not you can. And it's never taught to electrical engineers to have more than one. They figure, oh, it's good enough just to combine the capacitances, into one capacitor, and don't bother with two of them, and likewise with coils. Well, then why would we have center tap transformers? There must be a reason why. But it's more significant. We allow that much because you're not going to get the orchestration of overunity from a coil, but you will get it from a capacitor. You won't see the overunity except in the coils made manifest, but it's the capacitors that orchestrate it. They are the conductor of the orchestra. And you have to have a minimum of two capacitors. They have to bounce off of each other. And they have to be low enough in value, I prefer a tenth of a picofarad for each, for them to become prismatic in their interactions, so that some of the energy passes through and gets converted into reactive power. And every time it passes through, more reactive power gets converted from real power. And it doesn't come back out as real power. That's the difference. Because it's not absorbed and then discharged, which involves two delays, one for absorption and one for discharge. But when it refracts through the dielectric constant of the dielectric material, acting as a refractive medium, which has a refractive index, which is the square of the dielectric index, I believe, if I have it correctly, or else it's the square root. I may have it backwards. It's one or the other. It converts directly over. But it only works when the capacitance is a tenth of what's available on the market to buy. They won't sell you a tenth of a picofarad capacitor. But that's the magical area in which this refractivity occurs, in which the energy passes through and comes out the other side reactive, and it does not come out real by any means. And it's not just reactive. Actually, it's more than that. It's displaced by 180 degrees. It's that magical domain of separation of voltage from current by 180 degrees. So the capacitor has gone beyond the specifications of what we've been taught. It's beyond its lagging, lagging voltage by 90 degrees. I don't think I'd want to call it lagging voltage when it goes to 180, because it's really lagging current. In other words, the capacitor is behaving like a coil, but double trouble. Instead of merely the current lagging by 90 degrees, it lags by 180, because that would be reverse. That's true. Yeah, I'd have to take a guess, estimate, that the capacitor at 100 femtofarads behaves like two coils, two two reactances of a coil of an inductive nature, one on top of the other, to give us 180 degrees negative from what the voltage that was applied to the coil. That's my guess. But I don't know. All I know is it works. It happens. And as a consequence, time goes backwards to accommodate. See? So we're actually manipulating time to accommodate the reversal of current. And I think this is what happens when microcap does its calculations. It changes the time interval per interval based on how quickly change is taking place. It wants to make sure that the change doesn't happen too suddenly, because if it does, it'll give you an error message and freeze up on you and stop running. But if it decides it can still run with it, then it'll change, provided it changes the interval of time to accommodate such a rapid change of energy, or power, I should say, energy, whatever. But since it's changing the absolute value of the interval of time, it's also changing the polarity of sign. Is it positive or negative? And so the simulator doesn't know the difference. It doesn't know. It's just trying to accommodate the situation, and so it goes in reverse. And somewhere in the computations, the mathematical equations for manually assessing what's happening in a circuit that are taught to an electrical engineer, somewhere in there it provides for the sign to be positive or negative for time. I'm sure they're taught, oh, just discard the one for negative, it must be a fluke. But the simulator isn't told to do that. And so all of these simulations, because it can't. Actually, now that I think of it, because if you have a switch, a mechanical switch, you have to be able to create a surge, because switches are known to create surges, because they are capacitively parametric. Because the two contacts of that switch come together and come apart. I think I covered this already. So you see, it's hard. You can't get away from the reversal of time as a consequence of reversal of current. There's just no way to do it. You can't wiggle your way free from it. So this nice wave here is growing because of negative damping. But if you put a negative sign in this t over here, this time, this e, natural e to the power of time, if you make this negative, then it becomes positive damping, and the wave diminishes in amplitude. Anyway, I think I've talked enough. I'm kind of tired of this. Okay, go off on your own and give everyone a hug.